All right. Hi, everyone. This video is going to talk about the homework for RC circuits in HL physics class. Now, even though this video is meant for HL physics students who are in grade 12, if you're taking HL physics in 11th grade and want to get ahead, or if you're planning to take HL physics in IB, or you're just curious, then that's completely fine too. Keep on watching. All right, let's start off with question number 45. A 12-volt battery is connected across an uncharged 2.7 picofarad capacitor and an 8.2 mega ohm resistor in series. Sketch two graphs on the same axes to show how the voltage across the capacitor and resistor change during the first 30 seconds. All right, so we have some given values. We have the initial voltage, which is 12 volts. We have the capacitance of the capacitor, which is 2.7 times 10 to the power of -6 farads. We have the resistor, which is connected in series. So if we draw a diagram, here we have our battery, positive and negative terminals. We have a capacitor, and we have a resistor. This is 12 volts. This is 2.7 microfarads. And this resistor is 8.2 mega ohms. Right? So when the battery is connected across the capacitor, the capacitor is going to charge. That means that the resistor voltage will start off at the voltage of the battery and decrease exponentially over time. But since the capacitor is charging, its voltage, or the voltage across it will increase exponentially over time until it reaches the voltage of the battery. Now, if we want to sketch the curves, now that means for the resistor voltage, it's going to have this shape. And for the capacitor voltage, it's going to have this shape. In order to sketch these graphs, we need to find the expression for the discharge. We need to find the expression of the voltage across the resistor over time. And the first step in doing that is finding the time constant. Now, the time constant equals the product of the resistance of the resistor times the capacitance of the capacitor. Now, if we plug in our known values, 8.2 times 10 to the power of 6 for resistance, and 2.7 times 10 to the power of -6 farads for the capacitance, and we plug that into our calculator, we get tau, which is the time constant, equals 22.1 seconds. All right, the second thing we should do is derive a function for the voltage across the resistor as it varies with time. All right. If you look at your handy dandy data booklet, you see that the voltage across a resistor or a capacitor over time is given by the equation V equals V sub 0, which is the initial voltage times e to the power of -t over tau. Now, we know that the initial voltage, V sub 0, is equal to 12 volts, and that tau is equal to 22.1 seconds. Now, if we substitute those values into our previous equation, we get 12 times e to the power of t all over 22.1. Okay, great. Now, let's create a table in order to graph V of t for resistor and capacitor. All right, here's a table showing voltage in the first row and time on the second row. Now, the reason why I'm only plotting these up till 3 tau is because the question states that we only need to sketch until the first 70 seconds. Now, 3 times tau, and tau equals 22.1, is equal to 66.4. And since after 3 tau, the value of the voltage is basically 0, but not quite, then it will have a negligible difference to 70 seconds. So let's start plotting V when t equals tau, or 22.1 seconds, is 4.41 volts. Okay. Now for 2 tau, 2 times 22.1 is equal to 44.2. And this equals 1.62. Now finally, for 3 tau, as we've seen here, 3 tau is 66.4. And that equals 0.597. If the problem doesn't specify how many sig figs they want you to write, always go with 3. Right, since the maximum voltage is 12, I'm going to divide this up into intervals of 4, the voltage that is, and I'm going to divide the time axis into intervals of tau, which is 22.1. And 66.4. All right, now we can plot the values for the voltage across the resistor over time. Let's mark that in blue. So when time equals 0, the resistor has maximal voltage, 12. At tau, 22.1, there are 4.41 volts across the resistor. And at 44.2 seconds, there are 1.62 volts. And for 3 tau, 66.4 seconds, there are only 0.97 volts. And we can assume that it's basically the same for 70 seconds. Now connect the dots. And now you have the voltage across the resistor over time. Now since the capacitor is charging, it will have a similar graph, except that it's increasing exponentially and approaching the value of the battery voltage, which is 12. So we can just, therefore, it will have this shape. That's the voltage across the capacitor. All right, that's question 45. Let's move on to question 46. All right, here's question 46. It asks us, consider again figure 11.43. That's this over here from the Hodder textbook, which represents the discharge in an RC circuit. The value of ln I sub 0 was negative 9.57, and ln I was negative 12.4 at time 100 seconds. A, what was the initial discharge current? All right, since we're given ln I sub 0, but not I sub 0, I think the first step would be to linearize the expression for current over time in the discharge of an RC circuit. So in order to linearize any equation, just take the natural log of both of the sides. Since I sub 0 and the exponential term are multiplied together, that means the natural log of that whole expression can be rewritten as ln I sub 0 plus ln e to the power of negative t over tau. Now, if you remember your log rules, we can move the power of whatever is inside the log to the front of the log. And the natural log of e is just 1, so that's our entire equation there. All right, now we need to find the current when time equals 0. I equals I sub 0. Let's work with our linearized expression. T equals 0. So that entire term cancels out. And now we can use log rules to get rid of the log on the left side and rewrite the right side as e to the power of ln I sub 0. We are given the value of I sub 0, ln I sub 0, sorry, and that's negative 9.57. Now chuck that into your calculator and you will get 6.98 times 10 to the power of negative 5 amperes. Okay, that's I sub 0. Cool. Now, part B asks us to determine the time constant for the circuit. All right, since we're given ln I at 100 seconds, that's negative 12.14, I think it would be a good idea to stick with our linearized expression. Right. ln I is negative 12.14. ln I sub 0 is negative 9.57. Subtract that by 100 over tau. And this is 100 because ln I is equal to negative 12.14 when t equals 100 seconds. All right. Now, you move negative 9.57 to the other side. And now if you solve for tau, you're going to get 38.9 seconds. And the last question is C. If the resistance in the circuit was 820 kilo ohms, what was the capacitance of the circuit? All right, this is basically 3 marks. If you remember, tau, the time constant, equals R times C. And since we know both the resistance in the circuit and the time constant, which we just got 38.9 seconds, all we need to do is solve for C and plug in our value for the time constant, 38.9 seconds, over the value of the resistance, 820 times 10 to the power of 3. Plug that into your calculator and you get 4.77 times 10 to the power of negative 5 farads. Right, awesome. Okay, that was the homework for RC circuits and HL physics. I hope this video helped, and make sure to turn in your homework in time. Bye.